Okay. Sorry, I was not detecting my computer. So, right, this is where we left it, just before Easter. Yeah, if I remember correctly. Remember, we just had the last slides to finish lecture 7, and then we will complete today lecture 8. Okay, we will have time to finish, no worries. I'll make sure of it, and if not, we will just cut material, that's it. Okay, so just a quick summary of what we're going to do and so how we'll conclude. So today is the last teaching lecture of new material. So we will finish today with lecture 8, and we will see mainly information cascades and bubbles. That's how we're going to finish today. And then so next week, there will still be a lecture, but it will be focused on the final exam. So you know you have access now to last year's final exam through Blackboard. I uploaded the final exam and the receipt exam from last year. So what we will do next week is to go through the answers, okay? Or, well, all the possible answers to all the questions, and also the feedback and marking criteria that we gave for the different answers. So we will not upload answers, but the answers will be given during the session. Yeah? Okay. Right, so, let's start. So remember that we started to see the topic of behavioral economics, and we saw the different reasons why markets fail during the module, but we saw the different reasons why, kind of alterations to the uncertainty model or the models of behavior in terms of consumers. So the last concept, the concept where we left it last week, was in the law of small numbers that you have here. So one of the things that we do in economics is to randomize. So when you've seen econometrics, for example, we focus very important in to take a random sample. So you see, when we want our sample to have that Bell structure, that normalized structure, yeah? And the normalized shape is because that means that our sample is random. And why is that so important? Why is that so important for us? Because that way it means that we can have generalized conclusions. So we can actually extract from a sample from the general population, we can actually make conclusions for the general population, okay? And the reason why is that important is because we assume that within that sample, we have a combination of population, of individuals, of firms, whatever you are analyzing, of countries, okay, which represent, okay, the general population. But what about if actually within that sample, the individuals that you have are actually the ones, or the individuals or the firms that you are considering are actually the ones that have been specifically affected by one particular event. So it's actually not random. It's really biased, okay? And this is what the law of small numbers says. So then the influences, or then your conclusions, may be completely over-influenced. And this is really common, for example, when sudden events happen. And imagine there is a plane crash, okay? And everyone reads about it. Well, the probability that there is another plane crash is very slim, okay? It's very small. Yet there is going to be a generalized fear of a plane crash, okay? Because you are basing your, or maybe you've been involved in one, okay? Because you are basically basing your opinion in a very small sample of information. Or the example that you have in the test about you being unemployed, okay? Then in a very personal experience, you are basing some information which may relate to the national statistics of a country, but in reality this is based on the law of small numbers. Okay, so you cannot really draw conclusions in that very biased statistics. Now, this actually relates to the topic that we saw when we talk about gambling. Yeah? So it is very common in gambling in games, like people may overestimate their chances to gain money. Okay? And also, this is something that insurance companies, okay, when they set up their primes, their primas, they play with. Okay, so there are certain things that they may play with, and it's with fear, even though they know that the probability that certain things happen are very, very small. So many people, for example, will buy insurance against certain products, even though that the probability that there is a failure on these products, or the probability that they will lose money from these products, is very, very small. Okay? So this is because of the law of small numbers. Okay, so the last part also, which relates to uncertainty, and also that we've been seeing in this, not just in this module, but in microeconomics in general, is the way in which we consider cost, both as consumers and as firms. So when you've seen cost, there are certain types of cost which you've been told, or we've always been told, well, we don't consider sunk cost when we make decisions in the future. So if you saw managerial economics with me, or you saw Micro 3 with Mario, you will have seen exactly the same, or very similar information, hopefully. Now you will have seen that firms don't consider sunk cost when they make decisions in the long run, okay? Because these are costs that you cannot recover, yeah? So it's the same for people. Sunk costs that you spend and that you cannot recover, you don't consider them in the long run. But then, is that true? So don't you actually consider, we know that firm theory says that, okay? But do actually consumers rationally not consider sunk costs? So if I tell you that you are going to get certain specific money in the future, or now, don't you consider what's going to be the value of that money in the future? So we know money depreciates, okay? And so you will make economic decisions based on the depreciation of that money, okay? So in reality, you do, as a consumer, consider, or in your mind, you do consider that sunk cost. You do consider the depreciation of that money. And if you've seen finance, this is why when you see firm theory, we tell you, well, this is not the financial cost, it's the economic cost, yeah? Because in finance, you do consider the depreciation of this value, of these assets. Okay, so the way in which consumers then are gonna consider the depreciation of these assets is gonna depend, okay? And it could be also depending on what type of consumer you are. So in theory, and a simple way of looking at it could be that, well, consider that I give you £1 now, okay? And what's going to happen if I give you £1 now? The way that you are going to value £1 in 1 month is less, right? Because money depreciates just because of that. How much it is going to depreciate? Well, in 1 month, that pound will be valued by you by delta, being delta less than 1 pound. Okay, well, that depends. That delta then is the time discount factor. Yeah? So you have there the value now of 1 pound provided 2 months from now, then there will be delta times delta. Okay, the first delta for the first month, the second delta for the second month. So delta squared. So how much it could be the value of that 1 pound if in n months? So delta times delta times n, right? So delta squared n. So this is the way of exponential discounting. Now, assuming that you are an exponential discounting person, because actually what behavioral economics does is that, well, it also considers that consumers could discount money in different ways, okay? And another thing that it considers is like the way in which you discount money in the short run, it will be different than the way in which you discount money in the long run, okay? So given more power or given more weight to the money in the short run than in the long run, okay? So I wanted to come here. Okay, so then basically what this is saying is that that pound, okay, if I tell you you are going to receive that pound in the short run, in 1 month, right, the way in which you will value that pound, it will have a higher weight than the way in which you will value that pound if I tell you you will receive it in the long run, okay? You will discount it in a different way. So it could be that you are exponentially discounting it in the short run, and then you change the way in which you discount in the long run to, for example, hyperbolic discounting, which is another way of discounting, okay? So this also, you will have seen this in finance. So let me actually change to the visualizer so I can, now is when it doesn't change. Yeah, right. So in rational model discounting is usually done also exponentially, okay? So the present value that you give to that pound, right, would be equal to the future value 1 plus Rn, where R in this case, so this will be, for example, the one that you may find in normal, in common books, which this will be the discount rate, and this will be the period of time. Yes, so you may be used to more. And in hyperbolic discounting, K decreases as time progresses. So that will be the difference. So this is the difference between both of them. So you could be that in the short run you are exponentially discounting, which is the one that we saw before, and then in the long run you could be that you are hyperbolically discounted, or vice versa. It could be depending on the consumer. Okay, so you may be that if you see in finance, you are more used to the exponentially discounting one, in which you this is how you do it with the present value and the future value. So, and then some consumers, if they are hyperbolically discounting, the K actually decreases as the time will progress. So again, depending on the consumer, what behavioral theory is doing is assume that different consumers will discount time in different ways, but actually sunk cost will be considered. It is recorded, okay, what I write, so you don't need to take pictures. I will switch actually there, sorry about it. So, in fact, let me switch them, sorry. But it's quicker today. Right. So the thing about behavioral economics is an area which is still in study and in evolution, okay? You will see actually that a lot of things, especially for the lecture that we are going to see now, it is not something, the recommended reading, it is not on the book, but outside the book, okay? And you will have like articles and other lectures, one of them being a Nobel Prize lecture, because it's an area in pretty much development. Okay, so, and now how we are going to finish the lecture is actually seeing a concept which is information cascades and bubbles. Okay, so this was what we have left for lecture 7. And now I'm going to give you a little bit of a break because we are actually going to play a game. Okay? So while I switch lectures, I want 4 volunteers. It's very easy, okay? You don't actually have to do anything. So you actually have to do something, but it's not. Come on, can I have 4 volunteers? Yeah, come on. Come on, it's very easy. You just literally have to take a card from a deck, like, you know, and tell me if it is red or black. Like. I forgot to buy sweets, but like, you know, I'll give you sweets next time, okay? Like, okay. I'll remember that. Okay, good. One more, come on. Come on, very good, yeah. Thank you so much, okay. Right, okay, so, right, you see I have here 2 decks of cards, okay. One has majority of red cards, and the other one has majority of black cards. Now, I'm going to ask here this person to choose one. This one? Okay. But you don't know which one it is, okay? Right. So this is the thing. I'm going to shuffle it, yeah. So what we are going to do, so let's put player 1, 2, 3, 4. Right. You are going to select a card, and without telling anyone, neither them, which color card you've selected, right? Just looking at your card, you are going to make a decision, and you are going to tell me whether you think this is the majority red or the majority black deck card, yeah? Then you will give me back the card. I will shuffle them again, and then you will choose a card, and then just looking at your card, and remembering what his decision, so you, for example, he doesn't have any previous information, okay, but you will have his previous information, plus whatever card you've chosen, then you will tell me, oh, it is majority red or majority black, you know. It could be that you choose a red one and you tell me a black, or it could be, you know. So let's see if you manage to guess if it is the majority red or the majority black. Yeah? It's easy, no? Everyone knows what you're doing? Okay. Come on. Okay. Do you think it is there?
Red, majority red.
Majority red, okay. So I will note here that you said red, yeah? Okay. I'll make a note for me, though. Okay. I'll sample them again. Okay. So, yeah. You think it's red or black? The deck.
I'm going to say red.
Okay. Okay, so she said red. Yeah. Okay. You think it's red or black? The deck. You think it's black or?
Yeah.
Yeah?
Yeah, I think it's red.
You think it's?
Red.
Right, okay. Okay, can we give them a clap because they came in front of the class and they did really well, yeah. Okay, thank you, can sit down. Right, so, yeah, so yes, I saw everyone, it was the majority black, okay? And this was everyone's decisions, actually. So this is what they've seen, and this is what they said. Okay? And we'll explain now what has happened. So the first person saw red and said it was red. The second person saw black and said it was red. And we'll explain now what happened. The third person was very interesting because the two previous people had said red, but still decided to follow what she took, you know. And then, well, the fourth person actually took a red one. Two other people had said red, you know. It was a red person. And I played this game, I don't know, many times now, actually. And it always works in an information cascade. Okay, so today we are going to see actually information cascades, and we are actually going to work out a theoretical model based on the game that you just have played. Okay? So thank you very much, and for the next lecture, if you come to the revision lecture, I will actually bring sweets. Okay, sorry, I forgot. I didn't have time to buy them today. Okay, so right, so according to classical theories, we have seen, by the way, in case you are interested, my PhD was actually about this. Okay, my whole PhD was with information cascades in the film industry, in the creative industries. Okay, so according to classical theories, you have seen that consumers make individual decisions or independent decisions based on their own information, okay, and however, in many situations, you will have seen that what happens is like individuals observe the behavior of others and they modify their own behavior to follow the crowd. And you just saw this, okay? You just saw the simple cards with the games here, but you can find Actually, nowadays with social media, you can find these situations really often, okay? And I'll give you here an example, but you have so many things, so many apps in which this behavior can happen. Okay, there are two different concepts here. So social behavior, which is the main concept that we are going to talk about here, is actually the concept in which people follows or what we explained there, in which people not just follows the crowd, but follows the behavior of others, okay, or somehow adapts their behavior to the behavior of a society. And there are two concepts within social behavior that you will see in the literature. One is information cascades, and the other one is herd behavior. Now, there is a very small difference theoretically between them, but ultimately the outcome is the same. So the very small difference is like in information cascades, people follow the crowd regardless of their private information, so regardless of their private taste, okay? And in herd behavior, people follow the crowd considering their private taste. Ultimately, the outcome is the same. They follow the crowd. And for this reason, for practical purposes, we exchange them, okay? And this is what we are going to do for this lecture. So we are not actually going to consider the theoretical differentiation. But just so you know, there is a small theoretical differentiation. Oh, well, it's not particularly small, but there is this theoretical differentiation. In practice, it is particularly difficult to differentiate between them in applied economics. Information cascades, by the way, have been widely studied in markets such as, for example, the stock market, if you've seen any finance, housing market, firm decisions, okay? It's very common, they are very common topics in these areas. Okay, so let me give you, for example, another example, which is really common, and you may have actually encountered this. You have to, and this actually here you have another reference at the top. For example, you have to choose between two unknown restaurants, but you have no information about them. In fact, you may find that according to your food, to taste on food, you may like more the food of restaurant B, but you see that the restaurant A is more full, or you may go to TripAdvisor and you see that restaurant A has better reviews. So it's more likely, or in general, again, because obviously there are exceptions, that people will go to A just because it is more full. That's considered in the literature to be an information cascade. Because you are actually you actually believe that these people may have some information that you don't know, okay? Or some other information that you are not considering or you don't know about. Okay, so the question then in the literature, for example, regarding to this thing of the restaurant, is this rational behavior then, according to the classical theory, right? So do actually consumers in picture A have crucial information, or did they do exactly the same than you? Okay, did they actually see the restaurant, there were 2 people, they said, okay, I'm going to this restaurant, then there was 4 people, okay, I'm going to this restaurant, and just it's getting full and full just because there are more people, or just because it happened to have better reviews. Right, so maybe you are just following the crowd, these people didn't have actually more crucial information, and then in reality you are not following rational behavior. Right, so this is actually a very nice topic for a discussion question, not saying that you're having this discussion question, okay? But is this rational behavior, right? Okay, so how could you, how this, for example, this became even more evident because obviously this is not a new area of economics. So information cascades and herd behavior started to be researched in the 70s and in the 80s, and social network didn't exist then. So now it is a boom. So it's actually similar and it is comparable to the spread of an epidemic, okay, the way it works. And then, so how it actually works in terms of how it spreads information in this case. How could you calculate the probabilities of, for example, what has happened here with the cards game? How would you have, if I ask you, with information that you have now from the module, okay? Everything that you have studied now from the module. If I asked you, and all the tools that you have for all the economics that you have studied now with mathematics, econometrics, blah, 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 how could you actually go around what was the probability of the first person here choosing a red card and deciding it was a majority red or majority black compared to the second person compared to the third person? Could you be able to do that? How could you calculate that in an information cascade? Okay, so this actually relates to, obviously, mathematics. You've seen probabilities, but also to, for example, the concepts of uncertainty when we saw the flip the coin, okay? So it's a similar way of calculating the theoretical models, right? So see that there were two decks of cards. Okay, so we are going to see actually how the probabilities of the information cascade occurring with this game that we just saw happen. So there were two decks of cards, yeah? One, it was majority black, which is the actual one that your colleague chose randomly. And that was with probability 50%, and the other one was majority red, and that was also with probability 50%. Yeah, that was like do you remember the example of flip the coin? 50% probability or one of the other. Now, let me tell you that in each deck, in the one of the majority black, 60% of the cards were black, and in the one of the majority red, 60% of the cards were red, okay? Well, you could simplify that as 3/5, okay, but it's the same. Okay, so what are you then calculating here? So which rule are you using here? So what will be the problem of the first person? So they were selecting in a sequential order, yeah? So there was person number one, and person number one didn't have any previous information, okay? So this person for sure was going to make the decision based on the card that he selected, okay, because he didn't have any previous information. Actually, this is a very crucial person, because potentially the car that this person selects may be whatever anyone, okay, whatever deck they are going to say. It's going to depend also on the second person. So there is a probability that this person will select a red car or a black car, yeah? Because there are two types of cars, basically, yeah? Okay, so this person then will be the probability that he mentions, he says that it's the majority, he said it was red, no? So majority red, given that he selected a red car, yeah? Let's assume that instead with the black car we're playing with the red one, given that they said it was the red one. Assume, and actually you can do it then with the majority black, okay? So we do it with both, okay. So see, for the first one is the probability that it is the majority red deck, given that he selects the red car. Which rule is this? It's the bias rule. You've seen this for sure. Bias rule. I don't care if it is mathematics, statistics, or one unit. It's always the same, okay? It doesn't matter the example I'm going to give you, the bias rule is always the same equation, okay? So imagine instead of majority red, this is A, and instead of red, this is B, okay? So it doesn't matter. Okay, so how then do you calculate the bias rule? It will be the probability of the first event, which is, that is the majority red, which is 1.5, times the probability that actually selects a red car, given that the deck is the majority red, over the probability that the card is red. So in general terms, the rule of two independent events the bias rule of two independent events will be the probability of A times probability of B given A over the probability of B, and it's always the same. And you know all that probabilities, okay? Well, not the probability of red, but that's easy to calculate. So that's for person one. It's in the next slide, but I'm going to show you how to calculate it now. Okay, the probability that the deck is majority red is 1.5 times the probability that is red, given that the deck is majority red. Well, I told you 60% of the cards are red in the majority red deck. Okay, so that's 3 over 5, okay, or 6 over 10. Over the probability that the card is red. Now, the probability that the car is red is not 6/10. Why? Because in reality, for this first person in his mind, there are two possible decks, okay? And this person doesn't know which deck we are playing with, right? So the probability that the car is red will be, let me do here a note, will be all the possible probabilities. So the probability that we are playing with the majority red times, so this is just going around all the rules that you know about probabilities, okay, in your mind. The probability that it is red given that we are playing with the majority red, plus the other probability is that it is red, it is actually the majority black, times the probability that it is red and we are playing with the majority black. Yeah? So there are that two possible things, that it is red and we are playing with the probability, the deck that has majority red, and that is black and we are playing with the majority is black. It's recording that one, okay? So you'll have it in the recorded. So then the probability that is majority red, so the probability that is red would be 1/2 times 3/5 plus 1/2 times, and here, if we are playing with the majority black and the car is red, then 40% of them are red, so 2/5. So this is 5/10. So here it will be 1/2 times 3/5 over 5/10. So this probability is 3/2. Okay, and now what does it mean? Right, this person will actually say that it is a majority red deck if this is higher than 0.5. Yeah.
How can probability be more than 1? It's not correct.
You made a calculation yesterday. I think it should be 3/5.
Sorry, what?
It should be 3/5 rather than 3/5.
Yeah, it's 3/5.
So which one? Sorry.
The answer. First of all, 3/2 is bigger than 1.
So
Yeah, the
1/2
answer is
gives
3/5.
us 0.5 and 5/10 gives us 0.52. So they cancel out. What left is 3/5 instead of 3/2. 3/2 is
The last line.
Yes.
The-
The circle.
Okay. The circle is
1/2 gives us 0.5 and 5/10 gives us 0.5. They cancel out.
One second.
It's the circle one.
This one.
Yeah.
So right. Sorry, because this is. Is this because this is wrong?
No.
Because here I have it as 1/5 here. Sorry, 1/5 here. I have it. I think I made a mistake here. That's the thing. Oh no. Okay, this one is correct. Yeah, it's 1 over 5 anyway. Okay, so, okay, 1 second. Yeah, but this is 1 over 5.
This is 1 over 2. That's 1 over 2. Because that's actually what's that? 1 over 5 is 20.
This is 1 over 2.
No, the probability of red is 1 over 2. Because 5 over 10 is equals to 1 over 2.
Ah, okay. Yeah. Sorry. Yeah. So this is 1 over 2, you mean? Yeah. Of course. Yeah. Sorry. Completely true. Yeah. Completely true. Yeah, true. Thank you. Okay. Okay, and then this probability will be how much? 3 over 5. Yeah, okay. Thank you. Okay. And then it will still be higher than 1 over 2, yeah. Okay, we still have the same conclusion. Thank you. Yeah, I didn't see it, yeah. Okay. Right, yes. So anyway, the first person did the correct decision because it will still be higher than 0.5, okay? Which it was the probability that it was majority red. Okay, so after the break, which it took me 5 minutes to actually realize what you were saying, okay, sorry about that. Then we will see what was the problem for person 2, okay? Because it was different because it had previous information. Okay? So now 10 minutes break, okay? Yeah.
What does it mean by majority black?
The deck, the cards deck.
And
So I had 2 cards deck, one majority black and one majority red.
then what is like red?
Hmm?
Here, what is red?
Okay, so two things. One, about that, we are using the actual number of cards that there were in the game. Okay, so this thing that it says 2 red cards and 1 black card, no, we are using the 6/10 that I said just because this is the number of cards that they were on the deck. Okay, so that your colleague pointed it out. Well done, but I will correct the slides to point out that we are using the ones that we used in the game here. And second, I will correct, obviously, these numbers, which obviously will be now in the recording, but I will correct them to represent the real numbers. Otherwise, if you try to work it out at home, you will be like, what on earth is that? Yeah. Okay, so now what then is going to be the problem for the second person? So hopefully we will finish before the 50 minutes, so there are time for questions, given that it's the last lecture. Okay? Right, so then the second person, right, the second person had a different problem to the first person. Why? Because the second person had some private information, and by private information I mean the card that that person drew, yeah, but also had some observed information from the first person. So remember, the first person, she didn't know what was the card that the first person drew, but she knew that the first person had said that the deck was majority red, yeah? And then, what was the problem for the second person? Well, the probability that the deck was majority red, given that she drew a red card and the first person observed a red card. Yeah? That was the problem for the second person. And then obviously the problem for the subsequent people will be, and so on. Okay, then again, remember that the rule is always the same equation. Okay, so it's always the same equation, the Bayes rule. Right, so then it will be the probability of the first event happening, which is the probability that is majority red, which we know is 1.5. The probability that is red and majority red, okay, so the probability that the first person draw red in a majority red, the second she draw red in a majority red, okay? And then over the probability that the first card was red and her card was red, right? So remember that when we flip the coin, that we said that because the probability that it was heads and tails every time that you flip the coin were independent, in reality, so imagine the probability that heads happened the first time and the probability that heads happened the second time is the multiplication of the independent probabilities. Okay, so this is what we are going to do now. So in this case, the probability that the majority, the deck is majority red is going to be 1.5, exactly the same than before. But now the probability for this person, now this person is going to assume that person number 1 said the deck was red because he drew a red card. Okay, it doesn't have any other assumption to make, to be honest. So then remember that that was 6/10, yeah, 60%. So in this case, it will be again an independent probability if for her this event happening, assuming that she draws also a red card, otherwise the problem will change. And we will argue now what will happen if the event changes, okay? Because we will see now what happens if she actually draw a black card, okay? Then that could be different. What about the probability that it's a red car in general. Now we saw that, because you very well saw that, that was 1.5. Okay? The probability that in both cases was red, then again it's going to be 1.5 times 1.5. Now if you calculate all of this, and if I got it right, so this could be 36 over 50, simplifying 18 over 25. I'm pretty sure you can simplify more, which is 0.72. And over 0.72 is higher than 0.5. It's going to be always higher than 0.5, okay? But I will recalculate it. I just did it quickly. Okay, so the thing now, what happens though if the second person, instead of red, draws a black car? Which actually it happened that it drew a black car. Right here it can happen two things. One, that's because there is just one person ahead of her, then decides that that's not enough information to change her decision and says black, okay? Or two, it does follow the crowd. And then this will actually change the problem for the third person. Because in theory, the theory argues that if the first person says red and the second person says red, it doesn't matter which card the third person draws, that is always going to say red. Because as you can see from how the probabilities are working, this is always going to be higher than 1.5. But if this person says red and this person says black, so if both of them say different information, then the third person is going to be in a similar situation than the first person, because the information that it has ahead of her is 50-50, okay? So it's going to base her information on her private information. So we will be back to step one, okay? So the cascade theoretically forms with the third one. Now the question is, in a population, or for example in a class, okay, if we will continue with the game, we will not have hours enough, but we will continue with the game, could we form a complete cascade? Or could we actually have clusters? Okay, like for example in countries we can fly in clusters, okay, or in cities. And yes, we find that. And sometimes cascades can be broken. Right, so that's the second topic we are going to talk about: cascading behavior and clusters. Second and last topic. Okay, so it looks more complicated than it actually is, okay? So it is not complicated at all. In fact, the reference that you are going to have here is an actual book, and the book is completely easy-friendly. It's not very mathematical at all, okay? So it's just more like graphical than another thing. Okay, so cascading behavior says that a fraction of your neighbors switches to a behavior, and a behavior could be, for example, consumption of a good, okay? Then, so if enough of your neighbors switches to that behavior, to that consumption of a good, then the probability is that you will switch too, okay? Independently of your private preferences, or maybe taking into account your private preferences, okay? But your private preferences will consider social behavior also. Okay, so see here that a node, so these circles here are what we call nodes. Yeah, a node is a group of consumers. Okay, so each circle will be a group of consumers. Yeah, and assume, for example, if we go now to figure 2, that B and W, so these two nodes that are highlighted here, yeah, have adopted a behavior. For example, they have started to consume a good, okay, or they have started to adopt a specific behavior. They have started to recycle, okay? That's also to adopt a specific type of behavior, okay? And so the question is, will the node R, this one, adopt that behavior, okay? Will then the nodes which are neighboring adopt that behavior? Well, theoretically, if a fraction of R's neighbors adopt, then they should adopt too. So assume that R has D neighbors, okay, which is the theory that you have there. And then you have here the payoff for consuming this good A is A, which is positive, and the payoff for not adopting that good, continuing consuming another good, is this one, okay? Now, if a fraction of P neighbors adopts A, so that this happens, so 1 minus P don't adopt it, then it will switch. So assuming that, for example, the payoffs are 3 and 2, okay, then Q, which is exactly the payoffs, 1 second. So Q is a relationship of your payoffs, okay? Two over 5, okay? And this will be a relationship of the payoffs for consuming A or B. This could be consuming or adopting a behavior, okay? And payoffs could be profits or utility, it depending on who we are talking about. And then these will be neighbors, okay? So in this case for node R, 2, R has 3 neighbors, V, W, and S. Yes, so R has 3 neighbors, and 2 have adopted the behavior. So it has 3 neighbors, and 2 of them have adopted. So if this fraction of the adopted neighbors is higher than the fraction of the payoffs, then R adopts the behavior. Okay? That's what the cascading theory says. So R will adopt. And then you go switching node by node. If all of them switch, like it happens in D, then we say there is a complete cascade. But there is not always a complete cascade, and this depends on the links. And now we are going to see actually how sometimes it could be that the cascade can stop. Everyone can see how the switching behavior happens here? Yeah? I need a yes or a no to move on. Yeah? Okay. Okay, so we're going to see it here again. So, right, so this is a bigger community. Yeah? So we have a bigger community here. Yeah, so don't worry about this now. So see that you have all this community, you have 17 nodes, remember that each node will be a group of consumers. Okay? Now, you have two groups of consumers who have switched, okay, or who are consuming a good. Okay, so 7 and 8 have adopted. Let's assume that the payoffs are exactly the same than before, okay? So A equals 3, B equals 2. So the payoffs relationship, or the payoffs rating, is still 2 over 5, okay? So let's keep it simple like before, okay? Now, what we have to do is the fraction of neighbors that have adopted a behavior compared to the payoffs rating. Okay, so let's look then at node 5. Yes, so for node 5, so concentrate on this, don't look at the nodes. So for node 5, P then is, so node 5 has how many neighbors? 1, 2, and 3 neighbors, and 2 have adopted the behavior. Yeah? And this is higher than 2 over 5. So node 5 will also adopt. So it switches, yeah? Let's look, for example, at node 10. For node 10, it has, how many neighbors has node 10? 1, 2, 3, 4 neighbors. And 2 have adopted. This is also higher than the rating of the payoffs. So node 10 will adopt. Now, if you continue, as you have here, you can see that 4, 5, 6, 7, 8, 9, 10, all of them will switch. Okay? You will have all of that for that. But now, for example, let's see what will happen with node 2. Now, node 2 has three neighbors, 1, 2, 3, and just 1 has adopted. And this is less than 2 over 5. Yes, so node 2 will not adopt. And in fact, if you continue doing it, you will see that none of the others will adopt the behavior. So what happens in this case is the cascade adopts, and there are clusters, what is called, yeah? Because there is no complete cascade, and there are 2 clusters so there are out of the 3 clusters, 2 of them who will not adopt the behavior. Okay? So cascades actually can stop. They don't have to be complete. It depends on the influence of the neighbors. It depends on habits, on social behaviors, okay, on many things, and this will be actually studied by behavioral economics. Another thing that it could happen on cascades is that maybe a cascade is forming, or maybe there is a behavior that society is following and suddenly it's broken and it follows a different direction. For example, this could happen because of an expert opinion, okay, or because behavior switches. And this is kind of the shifts on demand, okay, or shocks on demand that you have studied from the start of microeconomic theory could explain or could be in line of these things. Right, so then behavioral economics can be influenced by external factors when making decisions, and this can actually be relevant when it comes to, for example, public policy. Yeah? And when do you think it could be, what types of public policy do you think it could be very relevant? This, like for example, environmental policy. Do you remember that we started the course talking about environmental policy? So let's just do a complete circle and finish the course talking about it. Yeah? So why is this going to be relevant? So think about, for example, what we said about adopting a type of behavior, no, a moment ago. And I said, like, for example, adopting a type of behavior could be related to environmental practices, okay? Could be about, for example, being more environmentally friendly or recycling, okay? And this could have a social influence, and so we could find that there is a cascade or specific clusters within communities, okay? So this type of behavior, okay, or the way in which it could be influenced, okay, the population in this sense, could also be a practice used by public policy because they know how cascades and clusters will work, okay? And for example, something that the good news about, and don't worry about this because we're going to talk about it in a graph, okay? So this is just for you to have the explanation, is about carbon emissions as negative externalities. So this will link about when we saw externalities, when we also saw at the start of the module carbon emissions, okay? So something that, for example, they do to deal with negative externalities of pollution that we saw in the externalities lecture is to put a tax on carbon emissions, okay? Now, the problem when you increase the prices on something for carbon emissions is that that will not always be reflected on a change of behavior by the population, okay? This will be the next slide. Why? Because will the tax actually incentive people to be more environmentally friendly? Well, if they do understand that the tax it is for being more environmentally friendly, maybe yes, but they may be just seeing an increase in prices. So something that public policy could do, and they do, is to educate people towards being more environmentally friendly. And this is actually using behavioral economics towards an understanding of public policy. So see, when we saw externalities, what we saw is that there was a marginal external cost from pollution. So what happens with this marginal external cost? So with this marginal external cost, then what we have is that the marginal social cost goes here, And then what we have is that the quantity produced, it is Q2, and so to try to reduce, they will have to impose a tax of all this amount, okay, so increasing the price of this good to try to internalize, okay, that externality. But what happens if we educate, you have at the end of the graph, with a bit of education, consumers, and not just consumers, firms, then they can realize they can save money by reducing their emissions. Okay, so not just tax them, because tax them they just realize, well, we have to pay a higher price. Okay, but if they reduce their emissions from the start, then what happens is that maybe their consumption would be, instead of Q2, Q3. So then to internalize this externality will be much lower, because first of all, the marginal external cost may not initially be this one, but this one directly. Okay? So if then you have a lower marginal external cost thanks to the education of people, then what will happen is that their consumption is lower, and then a much lower tax could sort out the problem already. Yeah? So there is a way also of taking an advantage of this behavioral economics on public policy and adopting behaviors in the society, educating people to going around the collection of taxes and, for example, things like this, like adopting behaviors and environmental policy through taxation. Does it make sense? So in this case, for example, the marginal external cost will be lower. And this is an actual graph, real graph from a paper. No, I didn't make it up. Yeah.
Question, is marginal
External cost?
equals to marginal social cost minus S?
The private. So you basically you discount it.
So is the curve representing the distance between MCS minus MC?
Yeah.
Okay.
Yeah, we saw that in lecture 7, maybe? No, 6. Yeah, 1. Yeah, 6. Lecture 6, yeah, sorry. Yeah. And then when you have a marginal external benefit, what you do is to add it. Yeah? Right, so there is a very famous, and actually, I'll finish with this. And there is a very famous Nobel Prize in economics, who is actually a Nobel Prize in economics, but he's a psychologist. But he won the Nobel Prize in economics, which is Daniel Kahneman, who it is won the Nobel Prize for his research in behavioral economics. And I uploaded the Nobel Prize lecture, okay, just for, it's not part of the exam, but just, you know, a module is not just about the exam, and it's an easy read, okay. So, and it talks about intuitive thinking, about rationality, and how actually that affects decisions under uncertainty. And then, and yet it's very interesting, okay, and how this affects reasoning. And it also talks about how we make decisions with a deck of cards, okay. So it relates to the game that we have talked about, and kind of brings together everything that some of the concepts that we talk about in behavioral economics. And it will be a nice ending. Okay, so I know we have 10 minutes to spare, but as it was the last lecture, I wanted to have time for questions. And of course, thank you very much for your time. Remember, you have the deadline for the blog post. Nobody forgets that. Okay, so you're more than welcome to go if you want, and thank you.